spin-adapted 2-electron spin functions. 2a minus spin functions. And let's start with spin operators in the first place. S plus does someone remember what S plus is? What's called a step-up operator. Well, that's the combination of Sx plus I times Sy, and correspondingly S minus is done with a minus sign here. And that sort of all is necessary because we know that the different components of the spin operator, they don't commute. So the commutator of Sx and Sy is actually I times Sz. And since those three, and you can sort of cyclically commute that around, x, y, z, x, z, x, y. Like always, like with all angular momentum things, you can cyclically commute them around. Since they don't commute, the commutator is not zero, it means they cannot have a common set of eigenfunctions. Which means that because we normally choose Sz being the operator, we choose the eigenfunction of Sz as our spin functions. Those spin functions, which are alpha and beta, and if you let Sz act on them, since the eigenfunction, you obviously get them back. And then what units do I use? In atomic units, yes. In atomic units, what's the eigenvalue for an alpha spin function? 1/2, right? And for the beta spin function, is then -1/2. Therefore, this is called spin up and this is called spin down. Right, so those are eigenfunctions, as said, but they're not going to be then eigenfunctions of Sx and Sy. Therefore, one defines those operators, these S plus and S minus, because then we know what happens with when we let S plus act, for example, on beta. As said, it's called a step-up operator. So, Nikolai?
You get alpha?
You get alpha, right. What those step-up and step-down operators for angular momentum generally do, they keep, of course, the spin quantum number, but they change the orientation spin quantum number, the ms value. And alpha is ms plus 1/2 and beta is ms minus 1/2. So if you let the up operator act on beta, it goes from -1/2 to +1/2. Correspondingly, if you do S minus on alpha, it goes down and you get beta. But what happens if you let S plus act on alpha? Yes?
Get 0.
That gives 0 because you can't go higher up. And S minus on beta is the same story, you can't go further down. Right. Now, what we want to do, we want to know what S squared, how to calculate the eigenvalue of S squared. I mean, the eigenvalue of Sz, that's simple, that we always can do. I mean, this is 1 electron functions, and in a second we'll look at the 2 electron functions. where of course then SZ is SZ for electron 1 plus SZ for electron 2. But we want to also look at S squared. S squared operator. Well, that is of course Sx squared plus Sy squared plus Sz squared. And then I can use those expressions, turn them around, and write Sx up as a combination of S plus and S minus. And correspondingly, I can write Sy using this as a combination of S plus and S minus. That then would be, for example, I would give 1/4 S plus plus S minus squared, because Sx is 1/2 S plus plus S minus, plus Sy is 1/2 divided by I, S plus minus S minus. So we have S plus minus S minus, then squared, and the I squared gives a minus sign. So it's minus 1/4. And then Sz squared. So that's Sx squared, Sy squared, Sz squared. And if you multiply the squares out and rearrange them, you can write that as 1/2 S plus S minus plus S minus S plus plus Z squared or you could, and that's the one we're finally going to use, you could write that as S plus S minus, S plus S minus, minus Sz plus Sz squared. And you could also use the signs in a different way around here, and then you get a different sign there. So the other option would be minus plus plus. Okay, so we have S squared. I obviously have S